All right, hello everyone. It is 12:13, so let's go ahead and get started. So this week we'll be talking about alternative consensus mechanisms. We've been talking before about proof of work, proof of stake, what traditional blockchains do, but this week we're going to look into what the problem is that blockchains are actually solving and what are other ways that we can solve this problem. All right, so you probably remember me from the first lecture. I'm Nadir Akhtar, the president of Blockchain Berkeley. I taught the first lecture, which gave a high-level overview of Bitcoin, of the problem that it solved. Today we're going to look into how other consensus algorithms can solve the same problem that Bitcoin tried to solve when it first started. So a quick overview of the lecture. We'll start off with distributed systems. We'll learn about what these things are and how blockchains are a part of these, and then move on to various consensus algorithm categories, starting with proof of something else, then looking at some implementation details of proof of stake, and then Brian will lead off with voting-based consensus algorithms and federated consensus. So to start off, how many people have heard of a distributed system before? Okay, that's about half of you. That's good. Can anyone give me a quick summary, one-line sentence of what a distributed system is? Go ahead.
They are not so centrally, but decentralized.
Yeah, that's a pretty good point. Right, so distributed systems are, in essence, a bunch of different processors that are storing information, but specifically, they can do two things. One, they can store some information and do some computation on the information they receive, and two, they can pass messages between each other. All right, so that's all that makes up a distributed system, in that you have some set of computers that have some ability to do computation and message channels that exist between the computers. All right, that's all a distributed system really is at its roots. The specific definition is debated from person to person, but in general, this is what people consider them to be. And the purpose of these systems is to accomplish a common goal. Right, they are meant to replace a single processor that is trying to accomplish some goal, because in the event of the failure of that single processor or single machine, you no longer have the capability to, you no longer are going to be running. Right? So in order to make sure that you can tolerate some failures while still having a system that works, we use distributed systems. And some properties of these systems are that you have concurrent components. You have components that operate at the same time in parallel, and that may operate differently based on the speed at which they operate. You have message sharing, which means that you can pass messages, you can communicate information between different processors. There's no global clock, because there's no central machine to say, here's what time you should all be considering. Instead, everyone's operating on a slightly different time because there's no central sense of time. And this leads to the fact that we can't make assumptions about what time restrictions we have on these processors. There's various terms like synchrony, weak synchrony, partial synchrony, and asynchrony, all of which describe protocols that make different assumptions about time, where full synchrony means that everyone's on the same page, all messages are shared instantaneously, and asynchronous means that there are no expectations on how long it takes for a message to be shared, and there are no expectations on how long it takes for a processor to finish some computation. And these terms are important because they help us design protocols and help us understand the flaws that come about with certain protocols. Right, and on top of that, we have the possibility for failure of individual components. So these are all properties of distributed systems, and these, as you may start to see, relate to blockchains in massive ways. So are there any questions first and foremost about these fundamentals? All right. Now let's talk about some of the properties that we want from a distributed system. So there's two categories of properties that we want from these systems, which are actually kind of like two properties that we want from anything. There is the safety properties and the liveness properties. The safety properties are the properties that say these things will never happen within the system. And the liveness properties are the ones that say these things will happen in the system. Safety represents the bad things that don't happen. Liveness represents the good things that will eventually happen. All right, so this is to prevent trivial systems. So to say where trivial means meaningless. Right, if we have a system that, let's say that we have some distributed system, and it all agrees on the majority value that's stored by some nodes, where these nodes contain either a 1 or a 0 at the beginning. If they all, and we want the system to find the majority value, they could all instantaneously agree to just not agree on anything. Therefore, they never agree on a false value, but they never agree on any value. So that's a meaningless system. It doesn't actually accomplish anything. On the other hand, if we want liveness, they could all instantaneously agree on 1 or 0 without actually caring about what the majority value is. In other words, doing something else meaningless that satisfies the liveness property that gets something done, but that thing isn't meaningful. Right? It's kind of like life. You can't just not do anything out of fear of something going wrong, or do everything out just to be super opportunistic and hopefully have something happen in the end. Right? You have to find a balance in between to make sure that the bad things don't happen and the good things do happen. And the same applies to these systems. So all the properties of these systems are phrased as either something that shouldn't happen or something that should happen. And when we have distributed consensus, all these different nodes trying to agree on some value, on some truth, to define the correctness of the system, we have to make sure that it achieves its intended goal. Right? So to ensure correctness, we use a consensus algorithm. And this algorithm needs to satisfy the following. It needs to satisfy validity, agreement, and termination. So let's think about how a consensus algorithm works in the first place. We have a bunch of nodes that are trying to agree on some value, whether it be the majority value, whether it be like some block. Right? In order for them to agree on some value that's meaningful, we need these three things. First, whatever proposed value they're agreeing upon must have been proposed by one of the processes. They can't just all agree on some arbitrary value. Otherwise, we don't have a meaningful system. And on top of that, they must eventually agree on the same value, all the non-faulty nodes. And this is to ensure that there is no lack of consensus. If they agreed on different values, then again, we have a meaningless system. We have a system that doesn't do us any good. And as you'll notice, these two things are safety properties. They refer to the things that will not happen. You will not agree on a value that was not proposed, that's not meaningful. You will not agree on different values if you're non-faulty. And on top of that, you need termination, which is a liveness property, which means that all nodes will eventually decide on some value. You need all three of these things in order to ensure that your system does something meaningful. If you don't have validity, then you can agree on some random value. If you don't have agreement, you can agree on anything. And if you don't have termination, you can never agree and still satisfy the other two. So having all three of these, it's what's critical to having a proper system. And again, keep in mind what you've learned about blockchains in general, about Bitcoin, about Ethereum so far, to see why these things matter. So are there any questions so far about these properties? All right. Glad to see we're all following along. The cap theorem. As an implication of these properties, we see that systems can't achieve everything. We see that they have to make some compromises in order to do some other things. And the cap theorem describes these compromises. It describes a fundamental theorem for any distributed system pertaining to the properties that it can and can't achieve. Where we have consistency, meaning that every node will provide the most recent state. If I ask some node, hey, what's the most recent state of the network? It will provide me with the most recent update. It will not provide me with anything less recent. Availability means that every node has consistent read and write access. If I try to write to some system, it will be able to do so if it's available. And if I ask it, hey, what's the most recent update, it will provide it to me if it's available. And partition tolerance means that the system works despite partitions in the network, where a partition is defined as some subset of the network being closed off by unbounded network latency. In other words, messages can't be shared between this subset and the rest of the network. And you'll see that we can only have 2 out of 3 of these. This magical little dot in the center of all these circles, that is what we call a magical fantasy land. Because lots of people like to claim that they can achieve all 3 of these, but it's actually impossible, and we'll prove it to you right now. So let's take these 3 categories and try to design a scenario in which we can have 2 and prove that the last one is impossible. So let's say we choose partition tolerance and availability. What we see is that we have a lack of consistency. Let's say this is a system that stores my favorite color. And first, I want to tell the system, hey, my favorite color has changed. Now my favorite color is red. I tell node 1, which tells node 3, but due to this partition, it cannot communicate the information to nodes 2 or 4. So when I ask node 2, what's my favorite color, because it is programmed to be available, it will tell me its most recent answer, which was blue, my favorite color from 4th grade. But you'll notice that we lack consistency. The most recent update was not shared to me when I asked this other node what the most recent state was. And because of that, we lack consistency. So we say, okay, let's switch out consistency, or let's switch out availability for consistency. We must lack availability. If I tell node 1, my favorite color is red, it updates, it tells node 3, still can't tell nodes 2 or 4. I ask node 2, what is my favorite color? To make sure that it is consistent, it will send out a message to every other node asking, hey, have you seen any updates since this time period? if it does not hear back from nodes 1 or 3, it will refuse to give me an answer because it knows that it might not be consistent. So it'll be waiting and waiting. It'll never send me the wrong answer, but it will never send me an answer at all. So this is one of the trade-offs we have to make. If we want both consistency and availability, we will lack partition tolerance. I tell node 1, my favorite color is red. It says okay, tells everyone else. Node 2 says, hey, your favorite color is red. Everything's great, but if we introduce a partition, we are falling back into one of the previous two scenarios. So this proves that we can only have 2 out of 3 of these different properties. And while we don't need to have them in extremities alone, like it's not black or white, we have just these things, we have to make compromises when we have, for example, network latency. Network partitions are like unbounded network latency. Network latency also leads to discrepancies in what the most recent state looks like to every entity. You don't have to just wait forever. Perhaps you wait for some period of time, like 5 seconds, 10 seconds before being available. But you still have to make compromises as to which properties you achieve at any given point. Right. So are there any questions about the trade-offs of these properties that we see in distributed systems? Anything at all? Yeah.
So if we have to sacrifice something, so what's usually being sacrificed?
Right. So that depends on the network, on the purpose of the network. Typically, we will not sacrifice partition tolerance because if we sacrifice partition tolerance, there's no way that there's no point in having a distributed system because it's not secure against these types of issues, about these types of disconnects between different processors. So, for example, Bitcoin will sacrifice consistency. Instead, you can always write to the blockchain, you can always produce a fork and have a different state than everyone else, but then you have this lack of consistency. If I ask you what your most recent state looks like, it'll look different from someone who's on a different fork of the blockchain. On the other hand, Tendermint, for example, which is a Byzantine fault-tolerant POS system, everyone votes on what the block is. There's never a fork, but because of that, you lack availability. You have to wait for some time before you're able to get that block in or to read that information from the network because it takes a longer time for everyone to agree on that single block. So it all depends on the goal of your system. All right. And then finally, the Byzantine generalist problem. So we've talked here about how consensus algorithm or how consensus works and how what we should expect from it, but we haven't yet described the problems that we run into when trying to achieve these goals. We've previously mentioned we have these issues in Bitcoin where we have all these malicious nodes, but how do we define this in the distributed systems context? Well, this is where the Byzantine generalist problem comes in. And you've heard of this in the last lecture, but we'll dive deeper into what it really means. Right, so the problem is ensuring that all of these different generals that are surrounding some city, all of these different entities, they're choosing either to attack the city or to retreat. They're choosing either a 1 or a 0 value, yes or no. How do we ensure that all the honest generals come to the same decision? If not all the honest generals come to the same decision, then some of the generals are going to lose when they try to attack the city because they will not have enough manpower. Spoiler alert, as you may have heard, is that we actually don't have a solution for 1/3 or greater corruption. And here's a very simple proof. Here's Lieutenant 1, Lieutenant 2, and a commander, all trying to agree on whether to attack or retreat, where the commander is the proposer and the lieutenants are followers. So the commander is honest. He tells both of his lieutenants we should attack, but Lieutenant 2 has been bribed by the city. He's been bribed such that he wants to avoid consensus within this network. So he says to Lieutenant 1, hey, Commander said retreat. Lieutenant 1 now sees 2 different views of the world. He sees the commander saying attack and the lieutenant saying retreat. So we say, okay, maybe it's this particular configuration that allows us to glean some information. Well, not necessarily. In the second scenario where the commander has been bribed and he gives 2 different responses, Lieutenant 2 honestly says that I heard retreat from the commander, but Lieutenant 1 still sees 2 different conflicting values. For both of these examples, Lieutenant 1 sees the exact same thing. He's incapable of distinguishing which of his peers is honest or dishonest. And it's because of this that we have no way to solve for 1/3 or greater corruption. And another spoiler alert is that Bitcoin actually is not 51% tolerant. In fact, you can see that nodes who gain 33% or more of mining power through selfish mining are able to dominate the network. They're able to start producing profits that are more than proportional to the amount of mining power that they have. So in any distributed system, you're incapable of protecting against 1/3 or more of the voting power. And if for some reason you find a solution, then you've solved also this Byzantine generals problem. And since this is not solvable by the proof that we saw here, it's not solvable for any system. Right? So a solution to all remaining cases in which you have like more than one or less than 1/3 of Byzantine faults in your network is practical Byzantine fault tolerance. This was a paper released in 1999, one of the earliest that described a way in order to have systems that could tolerate these faults. Right, so a definition of what we mean by these faults is that we have fail-stop faults, which are when nodes will just crash, messages will be delayed, but they'll never say something incorrect. They will always be correct about what they say, about what they communicate, and their processes. Whereas Byzantine faults include all of the above and the possibility to act in any arbitrary manner, to send corrupted messages or just incorrect values, to send conflicting messages to two different people, which may be intentional or unintentional. For example, we see that Byzantine fault-tolerant systems often exist in places where the machines are susceptible to like large amounts of like radiation, where the machine can be broken, corrupted, and now it acts in a way that was not expected. So these Byzantine faults are what we are anticipating in these blockchains, in these open, permissionless blockchains that anyone can read or write to, because there's no way to censor someone who's acting maliciously. Right? We want to design the censorship system. So are there any questions so far about the faults or about the Byzantine generals problem? All right, cool. So now we're moving on to proof of something else. After going over all that fundamental stuff, the Byzantine generals problem is the thing that we've been trying to solve all along. It's the thing that we've been trying to make sure that no protocol is susceptible to, and the way we do this is through making sure that voting power belongs to those who are committed to the network to make it expensive to vote. And proof of something else refers to all these different consensus algorithms where some resource is consumed in order to vote, which refers to Nakamoto consensus. Right? The something else is the resource that we consume, whether it be proof of work, proof of stake, or some other algorithm. Right, so you're familiar with proof of stake from the last lecture. Quick review is that we have validators instead of miners. We have certain people who are designated as trustworthy enough to sign off on the validity of blocks. And instead of burning work, we instead lock up stake. And that stake that we've locked up is what we use in order to gain voting power. So the resource here that's consumed is the native currency of the blockchain. That picture doesn't really mean anything. I just thought it was kind of cute, so put it up there. Proof of activity. Now this is an interesting one. Don't mistake this for the proof of work, proof of stake hybrid that Casper is trying to implement. Instead, it's saying that at every block, you do both proof of work and proof of stake before you validate the block. The proof of work part says that miners are going to solve and submit some block headers that may or may not have transactions within them. It depends on the implementation. But the point is that first you solve a block header, and then from there, you pass it on to validators who are going to vote on valid blocks, and then they'll sign off on those blocks, and then they'll receive rewards as well. So you consume two types of resources here. You consume proof of work and proof of stake. And I'm going to admit this type of consensus algorithm is often criticized, because once you've tied someone to some resource, do you really need to go through the work of adding an extra complexity to do more? Like we'll see here that we have I guess you have amazing security and maximum decentralization. Right? Buzzword salad, in other words. This doesn't really do anything meaningful because it doesn't provide any new security. It's a form of, I see it as a way to try to do something new and interesting, but it doesn't do anything meaningful because, again, once you've tied someone to some resources, you don't need to do that again. You've already secured that. Proof of burn is an interesting one. So an overview of proof of burn is that it's like proof of stake but edgier. Instead of locking up some stake and then getting it back after some time period, you burn it. You destroy the tokens, and in the process of destroying those tokens, you are given some likelihood of being able to propose a block or vote on a block. So the more coins you burn, the larger your voting power is. And the way we do this is through, as you saw in the third lecture, where you send some coins to some irretrievable address. You may have heard of proof of burn as a bootstrapping mechanism. Keep in mind, this is not a consensus algorithm, because this isn't how you gain voting power. It's just a way of making some altcoin have some value. So proof of burn, where you burn coins to get voting power, is a consensus algorithm. The bootstrapping mechanism says, if I burn some Bitcoin or some other coin, I can then get some random, other name coin, peer coin as a result. And by this, you're saying like, okay, if I burn 1 Bitcoin to get a million Dogecoin now equals 1 Bitcoin. And since Bitcoin has some fiat value, now Dogecoin by implication has some fiat value through these conversions. So it's a way for you to give your coin value. Most people don't like this in the community because you're wasting Bitcoin, you're destroying it, you're never going to be able to get it back, and it's already a deflationary currency. But it is some way to give your coin value. But that's just a clarification between the consensus algorithm and the bootstrapping mechanism. And the resource consumed here is currency, though it's not necessarily the native currency. Yeah. You have proof of space, which is an interesting one. This is used to, this is where you use your disk space in order to solve some challenge. Nowadays you use it for proving that you're storing some files on behalf of someone else. You may have heard of SIA, Filecoin storage. All of these are ways by which you can store information for other users and as an implication get rewarded. And through proof of space, you're proving that some space has been consumed, some storage space, and to store some file. All right, so this is how you can enforce a decentralized blockchain cloud storage. There's also proof of capacity in which you consume space merely to vote on blocks, but I don't see it as interesting given that proof of work and proof of stake have already pretty well done that. So the resource here that's consumed is the storage space. And then finally, proof of elapsed time. So we know proof of work to be a way by which we enforce this random lottery among people, among different miners who are trying to be elected to propose a block. Well, why do we need to burn this energy if we can enforce this random lottery in a different way? Why not spend time instead of mining power? So if you've heard of trusted execution environments or TEEs, these are machines that will run some code in a way that cannot be affected by any outside influence. And if it is affected, you'll see that in the result. It provides an attestation with every computation or with every output to say that, yes, the code has run in this particular manner. And should the execution of the code be changed, the attestation changes as well. So instead of actually buying mining hardware, you just buy this XGS, this trusted execution environment, and tell it to just sit there for some amount of time, waiting, just waiting. It just sits there, and you hope that the random number that it has chosen to wait is going to be in your favor. That's going to be before anyone else. So the first person whose SGX is going to finish waiting, they're the person who gets to propose the next block. And you base this on the assumptions of randomness and trust in the manufacturer, Intel. You trust that they have designed an execution environment such that it cannot be, there's no backdoor. That you can't adjust or affect the execution. Right, so the resource here that's consumed is time. And the reason you need this trusted execution environment is because you have to have a way that you can trust that someone has waited for this amount of time. Right, the whole reason that proof of work exists is because we want to force them to do some computation. We can't just trust them to say, oh yeah, I was burning this much energy for this amount of time. Right, so this trusted execution environment ensures that this waiting period cannot be altered. Yeah. So these are some of the various consensus algorithms that exist that are based on this Nakamoto consensus idea of consuming some resource to gain some voting power. All right. Are there any questions?
It's just stupid.
Go ahead.
So we go back to this picture of the lieutenants and the commander, which I like.
Yeah.
Which is very instructive. So basically what you're telling to the lieutenants is that you have to do some work which makes it really painful for you to communicate to one another. So painful that you will think twice before you lie. Is that the philosophy of all these algorithms that are out there today?
Right. Precisely. The question was, it's so painful, it's so expensive to be part of this voting process, to be part of the communication process of the consensus, that anyone who is not interested in the protocol or does not actually believe in the rewards isn't going to want to do this. And that's precisely the case. The whole reason why Bitcoin gives block rewards is because it's a reward for the honest miners. You wouldn't care about a block reward in Bitcoin if you didn't trust in the value of Bitcoin.
How is that theorem proof of stake going to be different from argument?
Yeah, so I'll dive into proof of stake in the very next section. Yeah.
Could you repeat why you thought proof of work and stake are better than proof of capacity?
Yeah, so proof of capacity, in previous implementations, at least in the implementations I've seen, is that it's difficult to enforce the storage. There's this one coin called Permacoin where you had to store some very large file among a bunch of different users. But the difficult thing is that you can't really change the file after you've asked anyone to store it. It's just going to sit there in permanent memory. If you ask everyone to change it, you have to now change everyone's version or like view of the file that's stored, so that's really tricky. So otherwise you're just wasting space the same way that you're wasting energy. Yeah. All right. Yeah, one last question.
With the proof of time, like,
yeah.
Does that work? I mean, why couldn't someone just calculate the solution quicker?
Right, so this isn't trying to calculate any solution. Instead, there's a sleep function that says it will sleep for some randomly generated number, and it's in order to enforce this random lottery between all the people who are doing this. Everyone has some random number, and the person who gets lucky by having the smallest random number of seconds to wait for, they're the ones who are going to be selected. And they say, yes, I was like given the opportunity to wait only 5 seconds as opposed to all of you who are waiting like 10 seconds. And because of that randomness in my favor, I'm going to be the one who gets to propose the block. So I recommend looking into it more yourself if you're interested. But the concept is just that instead of burning work, you simulate that mining through just sitting there and doing nothing.
Couldn't one person
Yeah.
potentially many people with that?
Sorry?
Couldn't one person potentially many people?
So one person could pretend to be many people if they had various different devices. Otherwise, you're limited to the single device that you own. Yes. All right. So proof of stake. So we talked before about how proof of stake works, about what you need to accomplish in proof of stake, the various attacks. Now we'll go into some of these specific implementations that exist within the field. The most two significant ones being Tendermint and Casper. So Tendermint is a mostly asynchronous protocol, meaning that it does not rely on time to a very large extent. It is a BFT consensus protocol with voting power denominated in validator stake. There's a two-stage voting process, and it favors safety or consistency, meaning that you need a large number of validators to approve of a block before it is allowed to be appended to the blockchain. This is used in the blockchain network Cosmos. And Casper is the proof-of-stake implementation upon Ethereum. And there are actually two different versions that exist. One is Casper, the friendly ghost, where ghost refers to the ghost protocol, the greediest, heaviest observed subtree. And that's correct by construction, so to say, in which you build it up based on these properties of safety that you want to achieve, properties of liveness you want to achieve, and then find a protocol that works within that realm. Whereas Casper, the friendly finality gadget, which is designed by Vitalik, aims to look at the existing protocol of Ethereum and transition it from proof of work into proof of stake. So it doesn't start from scratch, he rather builds from where Ethereum is currently. So to start off with Tendermint, it's a BFT-based proof-of-stake system. So if you recall the Byzantine generals problem, we have all of these different validators who have locked up some stake that are going to be voting in this consensus process. It is weakly asynchronous because you'll notice if you're able to read this chart, there's only one place in which time is mentioned, and that place is right here where it says invalid block or not received in time. So to go around for a circuit, let's say that we're proposing a new block. We propose the block, and then everyone is going to look at that block and decide whether or not the block is valid or invalid. And if they don't receive the block in time, they're going to go ahead and just vote invalid. So you wait for 2/3 of the validators to pre-vote on whether they think it's valid or invalid, and then from there you need another step to vote on whether you've seen 2/3 or more votes of valid or invalid. And then after that, you're going to commit if you've seen 2/3 or more of the pre-votes, or you're going to go to a new round to propose a new block if the block did not receive the necessary votes. And so this stage right here is for just saying, okay, I think this is correct. This stage right here is for confirming that everyone else has seen that everyone else thinks it's correct. This is referred to as a polka for whatever reason. I think it's just like an entertaining way to say, all right, everyone's going to like share this information again just to make sure that we're all on the same page. And then finally you commit or you go to a new round. You'll notice that with anywhere above 34% of the validator stake, you can stop consensus, but you can't actually drive consensus in your favor because you need 2/3 or more of the stake in order to make an independent decision without any of the validators paying attention. So that's why it favors safety. It'll first stop consensus will first stop before an attacker is able to drive consensus in their favor. All right, so it's energy efficient and fast because it puts some trust in the validators, these particular people who have locked up some stake, and this is excellent for enterprise blockchains where you have some sense of trust between entities, but you don't necessarily fully trust them. Yeah. And Casper is an idea more than it is a specific implementation. There are two different implementations or designs that are being examined by both Vitalik and by Vlad Zamfir, a researcher for the Ethereum Foundation. So Casper, the friendly finality gadget, is a chain BFT-style hybrid in which anyone can bond tokens, and there will be checkpoints as you go along the Ethereum blockchain where a validator is going to sign off, like every 50 blocks, every 100 blocks. Yes, everything from this point and below is finalized. I don't want to ever disagree with this truth. And eventually you'll shorten that checkpoint until it's 25 blocks, 12 blocks, 10 blocks, 2 blocks, until every single block is being POS validated, at which point you've weaned off the proof of work. Right, so by this, you're able to transition gradually and let the community go from one to the other. Whereas Casper the Friendly Ghost is a pure POS protocol. It ignores what exists in the current Ethereum protocol and says, all right, here's the things we want in the end. Here's how we can build a protocol that does exactly that. So it focuses on safety, and it'll maintain a validator set, an explicit validator set, rather than having anyone have the ability to bond tokens. So are there any questions about the Ethereum implementations, about how the different design choices make sense? Yeah. Right, so bonding, I mean staking, they're equivalent. Yeah. Mm-hmm.
One question is on the idea of finality.
Yes.
So I've heard multiple times that they say Tinder movement and also Neil, the BFT strategy has finality.
Mm-hmm.
It's a good thing. Can you explain that a little bit?
Yeah.
Why does Casper not have finality?
Right, so the question is, what does finality really mean? So finality is a way to say that this truth is never going to be considered invalid. In Bitcoin, you can have some blocks that exist, but if there's ever a longer fork, that longer fork is going to invalidate what you previously believed to be the truth. So in that sense, Bitcoin is probabilistically final. Like every transaction, you wait for a certain number of confirmations to have some probability that you will be included in the longest fork. But if there's some secret miners in Iceland who are building an incredibly long chain that is going to be longer than even the current blockchain since like 2010, and they were to propagate that chain to the network, everyone would be overruled. What you thought was final was not actually final. So that's the way it works in Bitcoin. But with these BFT-style protocols, anytime that 2/3 or more of these validators sign off on a block, on some update to the network, that and everything before it can never be changed. No matter how many people try to sign off on a fork. So you can never, in the protocol, change that. So it's final. It's 100% final. There's no probability to it. Yeah. And here Casper actually is final, hence the friendly finality gadget, which will say that this checkpoint here is final. Even if someone tries to fork, this checkpoint is going to be final and recognized as the truth. Yeah. Mm-hmm.
Is that for stopping people or self-mining?
Right. So that's one, to stop people from selfish mining, but mostly because you want to make sure that you never have to question whether or not a block is going to be included in the longest chain. Because if you do have to question that, then if you're trying to work with a blockchain like Cosmos wants to help blockchains be interoperable, if they say that some Bitcoin transaction happened, or they believe some Bitcoin transaction happened, and then find out, wait, it actually wasn't final, there was a fork. Now, in their own system, they no longer have finality, because now they're tied to something that's not final. So the finality lets you make assumptions about the transaction, lets you rely on the fact that it will never change, that this will always be part of the history. Yeah. All right, any other questions? All right, I will then pass it off to Brian after a quick 5-minute break.
So if I have one Bitcoin and I say I'm willing to burn a Bitcoin to get a million of these tokens, it says that the market value of these million tokens is 1 Bitcoin. Right? So if someone says, oh, I'm going to work traffic code is 0.95, then you lower the market value down. We say, oh, I'm actually looking for 2 Bitcoin to get the million. Now the market value is going to be just one thing market value. Right? Like I'm willing to lose this much value to gain this much. Apply that there are or something else.
Also, I was wondering if there was a way to check how many pieces that I had.
Yeah.
You might want to.
Yeah, I want to be sure because I wasn't sure if
they'll have.
yeah.
Okay, that's.
I just want to be sure that you weren't like that. No worries. I wasn't sure how long it would take to get there, but I would a lot of people or what were the hard questions that you there's some discussion you could accomplish when you're starting off this? I did. No, you're fine. I just want to go over it more like so introducing it before like here's what it's all about and choosing its values. I'm just curious to see what you think discussions have. I love discussion. Kind of interesting because I haven't left discussion. What's your style? So, it's way like 16A, 61A, a little bit just happens worksheet. I think okay, I can do that.
Okay guys, so we'll get started. So today I'll be covering voting-based consensus algorithms, which can be argued that are like the OG consensus algorithms because distributed computing has been around for quite a while. It's clearly, I guess, it comes earlier than a lot of cryptocurrencies. So distributed computing in most cases involves a lot of servers and a lot of computers trying to communicate and agree on values. So this is how people or computer scientists back in the day solved these distributed system problems or faults. So first of all, let's take a look at this really nice scenic photos that I found, or Rusty found actually. So we talked a lot about like these properties of distributed systems. They're all quite technical, but here I'm just going to tell you about on the western coast of Greece. There's this island called Paxos, right? People come here for tourism, people come here for yachting, and a lot of other things, right? And so Paxos is a Greek island, but did you know it is also a consensus algorithm? But yeah, it's actually a family of consensus algorithms. There's actually many different types of Paxos and different versions, and they're different implementations. But these are just a few main ideas that I'm going to talk about. So like I said, distributed computing has been around for a while, and cryptocurrencies aren't the first to use consensus protocols. So consensus algorithms are mainly used to have computers and servers talk to one another and maintain records and certain values. And naturally, Paxos was proposed in 1989, actually, by a really smart guy named Leslie Lampour to solve state-machine replication. What this means is, in like layman terms, it's basically different machines or different servers have different states. How do you replicate each other, or how do you replicate the data on a server in a, I guess, agreeable way? In the case that like a machine goes down, right? So we have these. The way that Leslie proposed it is the island of Paxos, right, has a legislative problem, and they have difficulties, I guess, coming up with, passing bills and I guess enforcing laws. So he comes up with the idea that there's proposers in this system on Paxos where people or clients request that an idea moves forward or proposes a bill to move forward. And we have an acceptor, which is a voter that votes on a proposal, and we have these learners. So after all the consensus finishes, these learners, learn the values from the end of the Paxos algorithm, and they relay this new message back to the client. And so we have this idea of a quorum, which is a majority of the acceptors in the network. And in order to come to an agreement, you need a subset of acceptors such that you have like 2 quorums that share at least 1 member. So multiple quorums need to overlap. I'm not going to go into too much detail about Paxos because it's actually quite confusing and quite like out of scope of this class. But the idea is that this protocol proceeds over several rounds, and these several rounds will help enable consensus and come to like some sort of agreement. And each successful round has 2 phases. So in each, in a general sense, the Paxos algorithm goes like this. So this client talks to the Paxos algorithm, and within Paxos, the client message that gets relayed, a proposer will come out and propose a proposal or a bill, and an acceptor and learner will discuss. And within the 2 rounds, or within the 2 phases within a round, they pass around ballots, and this ballot has this counter or a number that maintains the order that which proposals are, relayed, and the value that people want to update values to the, overall database, right? And at the very, very end of the Paxos algorithm, the learner takes in this final value and it relays it back to the client. So that's the main idea of Paxos. It actually goes through a lot of different steps, but in general, it's actually pretty fast. It has a pretty good performance, but it makes a few key assumptions. So this is the, early stage of consensus algorithms or distributed computing. So it's assumed that nodes don't try to subvert the protocol, meaning that you're working in a closed system, so you have some sort of trust within the system. You're only expecting these fail-stop faults, which are if your servers actually just go down. They don't actually account for if your server actually gets tampered with and starts spitting out random values. But in the real world, it's used to replicate large sets of data. It's actually used in these companies that I've listed here. Google has an implementation of Paxos for different data stores. IBM uses them, Heroku. Even WeChat uses it. They have an implementation written for it on GitHub, actually. But Paxos was a bit hard to grasp or hard to understand unless you actually really knew what you were doing. So people were like, okay, let's come up with a consensus algorithm that's a little bit more easier to understand, or more easy to understand and not as confusing. So it's designed to be more understandable than Paxos, and it uses this leader-based approach where every round, or in this distributed network, you have a leader that enforces all these, rules. It's easier to implement, or it's actually very easy to implement. There's actually a lot of different implementations of Raft written out there that people use for consensus, and even JP Morgan's Quorum, which is a a fork of Ethereum to use for their sort of network. They use some sort of Raft-based consensus, which is actually the etcd Raft implementation. So the joke here is that while Paxos is the island that is trying to come to consensus, this is the Raft that's trying to leave the island and move away from this confusing algorithm, right? The way that Raft works actually, so I talked about that it's a leader-based approach. This leader is really, responsible for many things. He communicates with the client directly, meaning that whatever the client relays to him, he will enforce. He's responsible for maintaining log replication on other servers, and if this leader leads until it fails or disconnects. And and in this case, a new leader is elected. And it has two main like algorithms behind it. This is just, I guess, a quick overview of what each algorithm goes through. So we have a leader election. This is how you select a leader. So leaders usually send heartbeats to other servers in the network saying that I'm still alive, I can still communicate with you. And once other servers don't receive a heartbeat, they know that, oh no, this leader just went offline. So in that sense, they start this election cycle, and each server starts an internal timer by themselves, and whoever is the first to time out this timer becomes the new leader, and they're able to enforce the rules that this old leader had. And log replication is when a leader accepts a client request, meaning let's say the client wants this leader to, I guess, update all the values in this network to plus or add 5 to all the values in the network or in their data store. The leader is responsible for ensuring that all other nodes have followed your request. So he'll relay that and tell these other servers or nodes in the network to do this, and then he'll confirm that they did it actually. So that's what log replication is, and that's a high-level overview of how Raft works. And next we have proof of stake. So the problem in proof of stake is we have this idea that the rich get richer, right? So large stakeholders can stake their huge balances, and they have a higher proportion or probability of being able to validate the next block and create the next block for the blockchain, and they'll reap in these rewards. So smaller stakeholders see fewer returns or lower returns, and it really centralizes the staking rewards in this proof of stake system. This is this problem that we're trying to solve. So how do we mitigate this problem actually? So we have this idea of delegated proof of stake. So you appoint delegates to secure your network on your behalf. What I mean by that is you have some sort of voting power to, I guess, elect delegates, and these delegates are responsible for choosing who can become the next person that writes to the blockchain or proposes a new block to the blockchain, which are called witnesses. So everyone has a proportional voice in the security of the network, but these delegates vote on witnesses to produce blocks. And if people don't like the behavior of these witnesses, they can actually get voted out, meaning that they won't be able to produce blocks again. So you don't always have this idea of large stakeholders always being able to mine the block or create blocks for the blockchain. You have witnesses that are either cycled around by delegates who vote on the next witness, or if someone's acting maliciously as a witness, delegates can vote them down and say that this guy doesn't deserve to be a witness anymore or a block producer anymore. And so the first DPoS system was actually called BitShares. It's a decentralized exchange platform that was started by this guy named Daniel Larimer in 2014. And it uses this idea of that the digital assets in BitShares, all these assets are backed by its core currency called BTS. And I'm not going to go into too much detail, but this is the first DPoS system that was, I guess, used or proposed, and I think it's kind of interesting. So any questions? Otherwise, I'm going to jump into federated consensus, which I think is a little bit more interesting. Oh, okay.
Just to understand how this voting would work, I mean, I guess that the nodes, they can communicate with one another through Reddit, through an open platform, or we can use closed communication channels. And then another question, wouldn't that always, over time, lead to the same people being endorsed time and again, as we have in certain Western democracies as well?
So which particular protocol are you talking about?
No, not specifically. I'm just trying to understand the concept of the delegated POS.
Oh, delegated proof of stake. So I guess, yeah, so your question was, how do you ensure that these people are cycled around, I guess, so that not the same people are voting again and again? It's the idea that, I guess, delegates can be cycled around first. So anybody in the network, as just a normal user or participant, they get to vote on delegates to represent them, right? And these delegates can actually be, I guess, cycled in and out. And so people can become delegates, and they can become not delegates, and they can. It's a process, but the idea is that you can, I guess, elect certain delegates to represent your voice or your voice or represent you. And when these delegates will, I guess, try their best to enforce that these witnesses or these block producers are actually doing a good job, or they're making sure that it's not the same people doing it over and over again. And if you believe that your delegate isn't doing the right thing either, you can also vote them out. You can also, the delegates are mainly responsible for voting out the block producers, but you as a, I guess, a participant in the network, you can, I guess, change your delegate to someone else if you really wanted to.
Is this a trust-based system, or do you need some trust?
I guess the idea is that you trust your delegate to represent you, so there is that some sort of trust in someone. But I guess in the overall sense, in the ideal case, everyone's trying to maintain the system of the maintain the integrity of the network, and you have to do that by having some sort of trust. Any more questions? Yeah.
So does some stake is being significantly voting for delegate, or like does every node has the same voting power when they choose delegate regardless of their
So
stake?
in my understanding, everyone has the same voting power for choosing delegates to produce blocks to become a witness. So these witnesses are block producers. They're trying to mine the block reward. So delegates are not doing any sort of, they don't reap in any benefits. They're just there for to maintain the system. They don't actually get any rewards. It's the witnesses or block producers that get a mining reward. And to become, I guess, a witness, I think you need to stake down some sort of capital or digital asset so that you can participate in the block producing process. But if you're a participant in the network, you have an equal, I guess, proportional chance of electing delegates to represent you. Yeah. Another question?
It was very similar to the last question. I was just struggling to understand what happens with the stake, because we're saying everyone has an equal chance of selecting the delegate.
So the delegate, I mean, they select the delegates to represent them. The people who are still trying to, I guess, compete for block rewards, those are still they're called witnesses. And to be able to become a witness or attempt to become a witness, they need to stake down some sort of digital asset so that they have a higher chance of becoming a witness. And it's up to the delegates to select the ones that are best suited for the task. So even if you like, let's say you stake down some sort of funds to become a witness, if people don't think that you're up for the task, or like if you, I guess, yeah, if they think that you're not up for the task, they can actually say that we don't want you to become a block producer, and we'll try again next round or something like that. Okay. Yeah.
So in a sense, delegates can choose someone with least stake to become a block producer?
Technically, you not least stake, but like they can try to choose someone to make it more of a fair and balanced process. Yeah. So we get to this idea of federated consensus. So in a distributed system, we have an idea of a quorum, which is a set of nodes that's sufficient enough to reach an agreement. So this is, in the Byzantine generals problem, the particular cutoff rate is around 1/3, right? 2/3 actually. You need 2/3 agreement to reach a Byzantine agreement. In distributed systems, the PBFD algorithm allows you to tolerate these Byzantine faults, as in if these nodes are faulty and generating bad values, malicious values, or just random values in general. But let's say, sure, we do come to a quorum, but what if I don't trust certain nodes in the quorum? Let's say Bob is in the network and I don't trust him because he didn't pay me back for boba last week. So how do we still achieve consensus, right? The idea is that in a normal Byzantine agreement, people already know who's already in the system, and they could entry into the system is unanimous, meaning that everyone already knows everyone in the system, and they can either trust or not trust, but they're forced to trust with the entire quorum that I guess votes on a certain idea, right? Or I guess opinion, right? And so we come to this idea of Federated Byzantine agreement, where how do we determine quorums in a decentralized way? So I'm not particularly a fan of like deciding on this quorum or agreeing just with the majority right off the bat. I want to trust the people that I want to trust, right? So we introduced this idea of quorum slices, which is a subset of a quorum that can convince one particular node of agreement. So individual nodes, such as me, I can decide on I only want to trust these 2 people or these 3 people before I guess my opinion is changed. So in this example, let's say I have a green crayon, but I'm colorblind. So I say, yo, I have this crayon and it's red. And then I have my friends that I trust wholeheartedly and they say, yo, it's actually green. And then, so like, because I trust them and they're enough to convince me that I guess my opinion is wrong, I'll say, okay, yeah, I agree with you guys, this crayon is green. And we come to consensus. So this is the idea of a quorum slice. And what do we actually want? What happens when we join these quorum slices together? We get this quorum intersection where quorum slices slowly come together and convince other quorum slices to come to the same agreement and forge a large quorum without having to independently trust everyone in this quorum. You just have to trust the people that you're doing business with. Otherwise, if you don't come to this quorum intersection, you get these disjoint quorums, which mean that you agree on 2 different things. So this like GIF shows what happens. You have 2 different quorums and they overlap, meaning that everyone comes to the same agreement. So let's go through an example. So I'm Brian. We're all hungry. Jillian and Nadir, we're all hungry, and I go like, hey, let's get lunch. Do you want to get pizza? And Jillian and Nadir go like, yo, it's $1 hamburgers today. Why would we want that? We have to get hamburgers. So they go, so in my, I guess, quorum slice, I need just Jillian and Nadir to tell me, to convince me that to change my mind, basically. So I hear them out and say, yo, you're right. Hamburgers are bomb. So I'll change my mind to hamburgers. And so we come to some sort of agreement within my quorum slice. Well, let's say Sarah comes along and says, hey, can I join too? So normally in a federated or in a normal Byzantine agreement, people can't just arbitrarily join the network, meaning that there's some sort of barrier to entry for these newcomers. In Federated Byzantine agreement, you can freely join. It's an open protocol. So Sarah joins, but she says, I don't trust Brian wholeheartedly, so I will only do business or I will only talk with Jillian and Nadir. And so they go like, okay, sure, let's form a quorum slice. So they do that, and they convince Sarah to go with hamburgers. Cool. So Alice comes along and says, hey, can I join in too? But I only trust Brian and Jillian. I don't actually trust Nadir or Sarah. So we go like, sure, let's form a quorum slice. And so we do that, and we convince her to go with hamburgers too. So in a sense that we started with 2 people that wanted hamburgers, and then we convinced like 5 people to go get hamburgers, basically. So slowly you can build up this huge quorum by accumulating individual quorum slices, and what that is able to achieve is you have this decentralized control. So no central authority authorizes consensus, and no one can prevent you from joining the network. There's low latency. This consensus protocol, even though I went through many slides, it's actually achieved in a few seconds. And flexible trust, meaning that you don't have to trust the entire quorum that you're dealing with. You only have to trust the people that you trust. And so you get to choose. You have the freedom of choosing whoever you want to trust. And who's ever heard of Ripple, actually? Yeah, cool. So Ripple is I'm just going to read, real-time gross settlement system and remittance network, technically. It's actually a distributed ledger across multiple financial institutions. Their focus is on big financial institutions. So these Ripple system allows banks to send money in overseas in real time and with low transaction fees because of, I guess, this consensus protocol. But they use a permission ledger, meaning it's not open to everyone in the world. It's only open to like the certain banks. But there's some sort of inherent trust within several banks, as in like we have banks in America that might trust each other, but you might not have them want to trust, I guess, banks in China. So they use this protocol to maybe come to consensus in that idea or sense. So you only have to trust whoever you want to trust. This is a picture that I took from the consensus process from their website. I'm not going to explain this. This is just a picture. But who's ever heard of Stellar, actually? Okay, cool. So Stellar is actually a fork of Ripple, but it's an open source protocol for exchanging money. So it's not only just for banks. It's a platform that connects banks, people, and other payment systems. And we have this idea of it's an open ledger, meaning that anyone can actually join. And their focus is on like the distribution of wealth, meaning that to try to like bank the unbanked, I think, something like that, where you have this open protocol where anyone can join, meaning that this Federated Byzantine agreement becomes more useful. So people can just trust people that they want to trust, as in the people around them, before they come to some sort of worldwide agreement, right? And this is an example that I ran through. It's actually the reverse of the options. We actually decided on hamburgers. In this diagram, we've decided on pizza. But if you want to read more, we have the article here, the Medium article on worldwide consensus. And actually, Stellar actually released a comic to like show off, or not show off, but like to explain how their consensus protocol works, but with like aliens and different planets, like how planets can come to consensus. So it's pretty cool. I recommend that you all check it out. So that's how Stellar works. Any questions? Yeah.
So with these federated networks, in practice, does this mean that like an individual person is going to have to like read like a list of nodes or institutions that they trust and like pick some, or is there another way to like randomly trust some group or something?
So the question was, how do you, I guess, select your I guess people that you trust, right? So I guess it differs in the two protocols. Stellar and Ripple have different protocols, but I know that in Stellar you have to compile your own list of like people that you want to trust. You want to have your sort of set of people that you trust, and you have to come up with that. I think in Ripple you're given one automatically, and so you don't have to, I guess, go through the process of finding which ones that you do trust, something like that. Does that answer your question? So they differ. The two protocols differ in a small sense, even though they're very similar. But you can enforce it either way. You can have you yourself choose whoever you want to trust, or you can have it already chosen for you, but still you can modify it however you want afterwards, something like that. It's just to make the onboarding process a little easier or more. Yeah. Question?
I was going to ask, couldn't someone from outside a quorum slice influence the agreement inside of it by some other quorum slice, like indirectly? I don't know, I'm just envisioning the structure.
So the only way that another quorum slice can, or either a person or another quorum slice can interact with another quorum slice, it needs to have some sort of overlap. Meaning that these people have agreed to like want to do business together. As in, if I go back to this idea, Sarah can't influence Sarah because she formed a quorum slice with Jillian and Nadir. She can't actually enforce. Let's say if I had a quorum slice with just Alice and me, technically they wouldn't be able to, I guess, interact with each other, meaning that they have two different opinions, basically. It's the idea that if we have someone within each quorum slice that can, I guess, mediate these two quorum slices, that's when you can come to an agreement. Or like you can have different quorum slices that influence each other when you have an overlap of like nodes in the system, or nodes in the quorum slice. If you have this disjoint or distinct quorum slices, then they won't be able to interact with each other because, one, they don't trust each other yet, but if someone comes along and mediates that process, then all of them can come to some sort of mutual agreement. Does that make any sense? Okay, yeah.
And if I understand you well, then in Ripple as well, the banks that participate in the system would have formed such quorum slices, like an Australian quorum slice or a European or American.
They could. That's the idea. I
They do
think
that in principle.
that's the idea for a federated business. So you create these federations that you trust independently, and these federations can somehow come to a mutual agreement. So that's specifically probably for Ripple, where they have, I guess, they've probably formed their own quorums with banks that they trust. Stellar's a little bit more different, or it is a little different because it's a more open protocol, meaning that anyone can join. As in, there's no barrier to entry because if you're a bank in the Ripple protocol, you need to be verified somehow because someone can't just masquerade as a bank and say, "Hi, I'm Bank of America. Can I join your network?" No, they can't do that. In Stellar, anyone can join. So the idea is to make it accessible to just a normal person, and the way that they do that is through this idea of creating certain quorum slices that allow other people to interact with each other and come to a mutual agreement. Yeah.
What I'm fascinated about here is that it could be constellations of power if you're very large federations, let's say all American banks or all European banks, that if you have such large federations, it would be rather easy actually to communicate and to determine what the outcome of a certain voting process should be time and again. Is that excluded in the system or could that be possible?
Personally, I don't know specifically about that. I'm not super familiar with the Ripple consensus protocol actually. I just know in general this is how federated Byzantine agreements work, meaning that it mediates the problem in normal Byzantine agreements where you have to basically trust this quorum that comes to a majority agreement. And in federated Byzantine agreement, you don't have to at least trust everyone in the quorum. You just have to trust people that you want to do business with or you want to trust. You get to select who's trustworthy or not. Any more questions? If not, then we're close to done. So last week we did assign readings, but this week is a little bit of, I guess, a recap. So we have a few overlap readings, but I want to, I guess, recommend that you check out the Stellar Consensus comic. It's really fun to read about. It's actually just a lot of pictures. And I would highly recommend also reading the Consensus Protocol for Stellar on Medium. And yeah, have a great day. We will have homework posted on Piazza this weekend.